If you haven't already, please sign in. Okay, so this is our second GBM of the semester. Thank you all for coming. So our first GBM was 2 weeks ago, last Thursday. At that meeting, we introduced everybody on the team, all of the e-board and all of the design leads. So today we're gonna dive in a little bit deeper into specifically what this organization does. So we have two main sub-teams within Swamp Launch. We have NASA SL and we have IREC. So each sub-team, specifically from them, will be talking more about what they're going to do for the upcoming semester and what their goal is. So there's a QR code on the screen. It's okay if you don't get it now. It'll be at the end. So we'll start with NASA SL, and our project manager for SL is Dylan Orgardowski.
Hello. For the QR code, you can just hold your phone up with your camera app open and then hold down on the QR code, and it should be able to pull up the link if you're on iOS, or I think Android does it too. But we are changing up our meetings a little bit. In the past, our GBMs have been a little bit more informative, but now we're transitioning more to technical design reviews for our GBMs. So really our goal with these GBMs is to A, get you up to speed on what the design is, but also B, for people to ask the leads and ask the team members specific engineering questions that they may or may not have thought of. So if you see anything that you're not sure about in the design that you think maybe they could improve, please feel free to speak up. This is why we're having them. It's not just so that you guys can get more up to speed, but so that we can make better designs based on the feedback and based on the concerns that we hear at these meetings. So with that, Alex, if you would like to start talking about the payloads design.
All right, so I'm Alex. I'm the payloads lead for the NASA student launch. And so what you're seeing on the screen here is actually my prototype for the payload. And so actually, Joel, if you go to the next slide.
Dylan, do you have control of the screen, or I've given you access? I need to figure something else out.
Do not think I do.
Oh, someone just changed the slide.
Okay.
Oh, I do. Okay.
Okay. So basically, nope, too far.
Wait. Who's control?
Okay. Well, so basically for this payload, there's a couple design objectives from NASA that we must meet. And so this is going to be a planetary lander, which basically means if you think of like the rovers on Mars, parachute down to the surface. That's pretty much the goal of this payload. And so because of that, we actually have to eject from the rocket from between 500 to 1,000 feet, which means we are going to be in the air and separate from the rocket for that descent. We then must land and become vertical to within 5 degrees of tolerance. And then once we are within that vertical 5 degrees of tolerance, we must take the panoramic 360 image, which if you see right here is a PyCam 360. And so right now that's our camera that we plan to go with. And then we must send the image wirelessly to the host computer. Next slide. Okay, so right now, as you see, we do have our prototype design, and we actually recently had our meeting on Tuesdays. So every Tuesday, my group members and I, we meet. And so what we did this meeting is we came up with some new designs that I asked everyone to review some new designs that I asked all of my team members to come up with over the week, and take some current design ideas that were given to us from other people and from our faculty advisors. And so what our faculty advisor suggested is added a Weevil shape to the bottom of the payload so that it has some passive operating ability, which is, if you see right here on the right, that's what that picture is. It's basically like a children's toy is basically what it's modeled off of. But basically, based on the way center of gravity works throughout the object, that it is actively self-righting on a flat solid surface. And so we obviously know that's not going to be perfect, but it's better than nothing. And so we are actually incorporating that into our design at the moment. And then one of our team members came up with a good design, which was actively have the Pi camera be on a 2 degree of freedom mountable servo type thing for the camera, which would basically allow just the camera to be oriented vertically with respect to the horizontal compared to just the whole payload. And this is good because it allows better, smaller, cheaper servos into the design and also more control. And so that's what we're working on at the moment.
Would NASA accept that as having the payload itself be within 5 degrees of vertical, if only the camera is?
We were having the more of it as a option of last resort, like to help us get within that tolerance and not be the only method, because obviously it can't correct for everything, but we were concerned about the precision of the other servos on the payload with it getting stuck or something. So we were looking into it as a backup option.
So pardon my ignorance for asking this question. What does NASA define as the payload? Is it everything that is released at deployment, or is it solely the mechanism of the camera?
So I think technically in the PDF, it really wasn't clear on what they defined as vertical. And it's something I'm really good in. That's my main question I have for NASA is like, because obviously depending on your design, you can define vertical as different things. And I don't think they were very clear on what has to be vertical as long as the picture had to be vertical. I don't think they were very clear on that.
Do you have any ideas how you're going to make sure that the payload is going down this way instead of like sideways where the camera can't really point? Is it just pointing at the inside of the team?
I think, Dylan, if you want to go back to the first slide where I have an image, the image of the whole payload, I can explain more of how it works. And so basically what we have at the moment is, if you see those by the legs, there's some like ellipsoid type things. That's how the parachute is going to be attached. So we're going to attach the parachute directly to the top. And so hopefully that will allow us to land vertically. But in the case that it doesn't happen, that's what these legs are here for. And so those legs actually are attached to very high-powered servos, as you can see down at the bottom. And those high-powered servos will allow, in conjunction with the legs, will allow it to flip over in case it does land sideways. So that is the current design. And then the Weeble will actually help it even more. So we're trying to incorporate different methods into getting it stabilized, because we know there's a lot of variability. And so we're working on different options.
In case it's windy, is there going to be a way for it to release the parachute so it's not getting dragged along?
So we were discussing that actually. We haven't thought up a way to do that because I don't know how NASA, I mean, we're not allowed to use explosives, and I don't know how well NASA would take to having flying knives on there. And we didn't really, so that's a couple questions I have for NASA is, can we, because I would like to just use a knife to just, you know, have like a spring-loaded knife and cut it. But I don't know, but also I feel like there's a lot of safety issues with that. So I need to consult with NASA on that one as well.
You don't necessarily need a knife. You can have like just a pin that is going through the fisheye that this is attached to. And then when we land, you could just rotate a servo to.
I know NASA last year had issues with just a single pin and a rotating servo, that they did not appreciate that design last year. So that is why, like, I did think of that, but they didn't appreciate it. They required it to be very over-engineered because they're concerned about the pin breaking or the servo breaking and releasing the parachute prematurely. So they normally want something. a little bit more concrete.
Use a solenoid. So a magnetic electric
Yeah.
actuator that drives the pin. So you can't use a servo in a single pin or whatever. So just have it be something where when it's energized or whatever, or even better, when it's not energized, it's engaged. And then when it
Yeah.
lands, it clicks a switch and it disengages, it applies power to the solenoid, releases the pin so the parachute blows away. So that way it's a fail safe. It'll fail in a situation where the parachute cannot come off.
Yeah, that is a good idea. I have not thought of that.
And just to go back to the camera, I noticed that you did move back to the PyCam. Is there a reason you used this over your previous camera system where you had like a separate lens and camera?
The reason I'm using this camera is for ease. Is I've decided based on the bit rate and the Raspberry Pi processing speed, I looked into it a little bit more, and I was concerned with the whole programming aspect of the Raspberry Pi and the difficulties that would present versus just having something pre-built do it for us already. And then also our other faculty advisor, I'm pretty sure, expressed some concerns as well with it, the method, because I know the image quality is not the best with that. So it was also prone to, it looked like distortions. So we were just looking for a cleaner image, and this was easier and required a lot less programming effort for the team for not that much increase of cost.
What's the actual like egg-like shape being held by? Like, is it by wires or like how do you make
for
sure
the Weeble?
Yes.
We're thinking of a combination of, because of screws in the bottom holding it in, as well as epoxy.
Would it be able to move if it's epoxied in, or?
I don't think I'm understanding your question.
How do you make sure the Weeble can move to the side and stuff? Like, how are you attaching it to the actual payload as to where it can move?
Oh,
like
the
that?
Weeble itself is part of the payload design, so it would be just the semicircle just be on the bottom. It's like part of the design itself. It's not separate.
So would you have weights inside of the Weeble?
I was planning on putting the batteries in there, and then because the batteries right now are the heaviest part of the payload besides the structure itself. And so by putting the batteries in there, it should help move the weight down there. And then from there, we would actually have to do the weight calculations once we have everything configured and a lot of testing, and add ballast weights to configure it properly.
Okay, so this isn't going to be like the 90s toys, like Mighty Beans, that have like loose weights in the bottom. So I think that's how they like effectively align themselves vertically.
The way I was reading it from the map is basically the center of gravity moves over the pivot point. And so it didn't really have to do a lot with the beads and more of where the center of gravity of the system was. So that's something that's actually being modeled this week that my team members and I are working on. And so, as I said, right now what our team is doing is we're doing a lot of SolidWorks designs, getting these catted up so that we can start the modeling, because we need, as we said, we need the weight center of mass calculations, for the Weeble. We need to make sure that works. We're testing out to see whether the rotating arm for the camera would be a good fit for the payload, or if it would be too constricted in size, and whether it will even work. And then also right now we're researching into the wireless picture and data transmission, because our issue with that right now is how we're going to do it. Because if we use what we currently have right now, which is just like a standard radio receiver, we're currently limited to 8-bit transmission rates, which for a picture is going to take a hot minute to send the image. And so our faculty advisor told me to look into VTX, which is basically what they use for FPV racing drones. And so the problem with that is it requires amateur radio license to operate legally. And so that obviously that becomes an issue for a lot of team members if we actually have to do that. And with the current situation, you have to take these tests in person. And so I'm trying to avoid that at the moment by not using that, but it definitely will be our backup just in case. And then right now we're also, once we decide on what video transmission, we're going to make sure we get our wiring diagrams done to make sure that all the pins actually line up with what we need, because we don't want to overuse one pin or have two different components using the same pin. You know, that would cause a lot of issues. And then we're also making sure that once we get the final weight, we can calculate the torque and the stress on those legs to make sure that it is actually capable of lifting up the payload in case it gets landed on its side.
And did you figure out what specific kind of altimeters or what components you want to use for your sensors?
I do have the list of what I want to use for, I did have, it was, for, I know I have the gyroscope and accelerometer picked out. I have the camera picked out, obviously, the board. I'm still trying to figure out what's the best GPS sensor to use.
Just a heads up on the ham radio thing. The licensing, you could do it online. It's like $15, and it's like a 500 question-ish like test bank that you could kind of just study through. So I wouldn't use the ham radio test as a limiting factor for the design, because you could finish that in like a day or two. And if you have even one person on your team that's ham certified, you could say they're the radio operator, and as long as they're at the launch, you can use whatever ham radio like tools you need.
I must have been misreading it because I thought the test had to be taken in person.
No, if you go on, I'll send you a link later. But yeah, I took it online.
Okay.
Literally like a month ago, I think.
Yeah. Also, if you're getting your certification for something like this that is critical for the team to be able to function, pretty sure we can convince the department to pay for it for you, so you don't have to pay the $15 out of pocket.
Oh, it was more just the in-person thing was like the limiting factor, because
Yeah,
I thought
no.
it had to be in person.
I completely understand. I'm just saying, like, I remember when I was an undergrad, $15 some weeks was my food budget for the week. So, like, if it push comes to shove,
yeah,
I'll get it paid for you guys.
Yeah, so we're still working on, because it might have to be that way. So we're working on how to get that wired with the board we're using and with the camera, because the way the Pi 360 cam works, I don't know. It didn't seem like it would be able to directly interface with a VTX card, and we would have to figure out a workaround. So that was the other issue with using the VTX method.
All right, well, we're going to go ahead and move on to the flight dynamics team. Let me see if I can.
And that's it, yeah.
Okay, Matthew, if you would like to take over and talk a little bit about the rocket design.
Sounds good. So, guys, I'm Matthew Estenos. I'm the lead on the SL Flight Dynamics sub-team. So I'm just going to talk to you guys a little bit about what we have so far, what we're currently doing, and what we're going to plan to be doing. So if you remember when we introduced Flight Dynamics, there were sort of two parts of it. There's the propulsion system as well as the retention system for the propulsion. And on the other hand, we do modeling and simulation. So those are sort of the two parts of Flight Dynamics. So let me start my video. I don't know why I didn't have it on. So right here, what we can see is a motor retainer. So this is the one that in our current design, we're planning on most likely using. So it is a flanged motor retainer. So basically what the motor retainer does, just to give you some background, when you have the motor in the rocket, basically during flight, we don't want it to move along the length of the rocket. We don't want it to move axially. We want it to be secured in place. So the motor retainer pretty much allows us to do that. It allows us to secure the motor so that it basically doesn't move out of position. So there are a couple of different motor retainers that are available. The flange you can see is sort of where there are the holes to screw in. That's what we mean by the flange design of it. And there are some that are not flanged. So basically the difference is what that screws into is called a thrust plate. You can see I also have that on this slide. So basically what a thrust plate is, it helps transmit some of the loads of the thrust. So basically when the motor is going and the rocket is generating thrust, that can put a lot of loads on the structures that are attached to the motor. So in this case, it would be like the centering rings, which are usually pretty thin and are could be subject to shearing forces. So that wouldn't be good if the centering rings for the motor failed. So basically the thrust plate allows us to redistribute some of that force and the stress so that it can be distributed more over the body of the rocket. So it's not putting those more sensitive components in danger. So we have the thrust plate and the motor retainer. And those little holes in the motor retainer, that allows us to basically screw it and secure it to the thrust plate. So when you think about a design that does not have that flange component, it would basically need to be secured to the thrust plate in some other way, maybe glued with adhesive or something like that, which is not as ideal because then if we want to take it apart to maybe better be able to access the motor and things like that, then it would be a lot harder to do that as opposed to just unscrewing something. So that's really where the motor retainer design comes in. In terms of the actual motor, we've evaluated a couple different designs using simulation, which I'll get into in a little bit. But right now, we're looking at the L1150, which is an L-class motor, so that's within the limits of the competition, so that's completely legal. And it's actually one of the weakest L-class motors in terms of the total impulse it delivers, so how powerful it is. And that's because in the current design and the current simulations, we're sort of on the higher side of where we want our altitude to be. So when we've been evaluating motors, we've sort of been trying to scaling down the power of the motor to sort of fine tune that. And so right now we're thinking the L1150 is a pretty good choice. And as the design matures, as the other systems mature and we get better weight estimates and things like that, and overall can model the rocket better, then we can make more finalized motor designs based on the simulations, of course, again. So you can go to the next slide, if that all made sense.
Joel, can you move to the next slide?
Sorry,
Letting me.
I accidentally closed the screen.
So now we can talk a little bit more about the modeling and simulation side of flight dynamics. So that picture you see on the bottom, that is sort of the model of the rocket right now in OpenRocket, which is a software that we use to run simulations. So you can see it's sort of a 2D schematic view right there. And within it, you can see there are quite a few different components. So those are all put in based on really what the structure of the rocket is going to be like. They don't look exactly like what those components are going to be like, but it's more like symbolic. So we have their weights, we have their positions, and as well as their size, so there's no interference. And we can place them along the rocket. So when we run the simulation, it takes into account those weights, where the weights are distributed, things like that. So when we run the simulations, we can get a couple different important parameters, which is what we've been doing. And we basically need to match those up with some of the requirements that NASA gave us in the handbook and basically make sure we're satisfying the requirements. And yeah, so basically just to go into those, I made a little table right here to sort of illustrate some of those things. So the apogee altitude is a very important parameter for the competition. In terms of the altitude that we're allowed to reach, it can be between 3,500 and 5,500 feet. So that's our max altitude. So as a team, we'd like to be close to the 4,500 feet just because that's a good middle value. So we're not too close to either of the extremes and in a way then too close to being disqualified if something goes wrong. So with the current design, with again the motor that we have and the current model that we have, it's predicting an altitude of around 4,820 feet. So it's a bit above that 4,500 feet. But one thing that tends to happen as the other systems mature, the weight of and we realize, just the whole design matures as a whole, things end up weighing more than we thought they would. We take into account more components. So the weight becomes more and that ends up lowering our apogee altitude as we progress through the design, typically. Typically that's what happens. So we'll continue to reevaluate that basically as the design moves forward. And we'll keep on evaluating whether this motor is the correct choice, or maybe we need to go to the next step up, or maybe the next step down. So that's sort of the decision-making process we have. And right now we're doing that through decision matrices or design matrices, our sub-team. So it's sort of a formal process where we can decide things like that. another factor is the stability at rail exit. That was another parameter that we had to pay attention to. So the launch rails, as soon as the rocket leaves the launch rails, it has to have a certain level of static stability, a static stability margin, and that's determined by that's a function of the center of pressure location, center of gravity location, the length of the rocket. So, but basically we can determine that through running simulations. And so that's another value we can get. And you'll notice that as a target, we're looking at 2.5. Now NASA requires a 2.0 static stability margin. So the 2.5 is really for sort of a factor of safety. We also don't want it to go too far above 2.5 because then we're in danger of overstability as opposed to understability. So once we get like to 3 and keep going after that, we also don't want to be overstable. So that's why 2.5 is a pretty good target right now. And right now it's at 2.26, which is not bad. It can be improved, but the main thing is we don't want it to move dangerously far away from that, from the 2.5 as our design progresses. The two final things that we're looking at in terms of major things, Mach number and velocity at rail exit. These are both about the speed of the rocket. So the rocket cannot exceed Mach 1. Right now, again, this is another thing we can extract from the simulations. We're looking at around 0.589. And in terms of the velocity at rail exit, so that's like the stability at rail exit. It happens at that point. We need to be at least 52 feet per second. And as of our current design, the current simulations, we're looking at 79.3 feet per second. So really with these, it's a lot simpler in that we just need to be above or below these values. We don't have to worry about over versus under being really bad as long as we meet these values and say as low, and yeah, pretty much have a good factor of safety would be ideal so that we're not cutting it too close to any of these values. So that's sort of the basic overview of some of the values that we look at and some of the things we're constantly reevaluating as the design changes so that we can see basically what other things we need to change as things progress in other systems and in our own system.
Quick question, Matthew.
Yeah, go for it.
What diameter is the rocket, and is there ample space for the payload?
So it's a 5.5 inch diameter rocket. Right now, you can see the so the payload. It's in the model. I don't know if you guys can see. It's one of the boxes, and inside there's like 2 yellow ovals, one inside each other, yellow or orange ovals. That's represented by the payload. So as of the current estimate I had for the payload, it would fit within that diameter of rocket. So we were initially going to use a smaller diameter just to account for the payload to give it some more room. That's why I went to the 5.5 inch. And yeah, so as of right now it should, but we can continue to reevaluate that if anything changes.
Yeah, I'd just say make sure that the parachutes, the ejections, and the payloads can all fit in that forward fuselage. Because I mean, if anything, you can always just make the aft fuselage smaller and the forward larger to like make more space and just account for it. But just something to know.
That was an issue last year because when during manufacturing, I made an error and accidentally made our forward airframe like 2 inches too small. So if that doesn't happen again, planning should help mitigate that error.
Cool. Yeah, in terms of parachutes and stuff, you can see those are also modeled in there. So as to the current estimates, the amount of space is accounted for in the current model.
Is that still the? Oh, go ahead, Bryce.
Yeah.
You're muted.
Oh, whoopsies. How are you positionally like placing your payload in? Are you gonna push it into the tube and try to find the holes for the shear pins, or are you gonna have some sort of coupler to stop it from going all the way in? Or what's your plan with that?
So as of right now, that's not really something I've been considering too much at the moment. So that's something I'll continue to evaluate, and I can work with Payloads on that, how they feel it should be best positioned for its ejection and everything like that. Right now, I mainly accounted for the size that we've estimated that needs to be packed in, and sort of the positioning there so that it has room basically within the design. But that is something that I'll definitely be working on and communicating with Payloads to make sure everything is optimal for both of our designs.
And that is something that Colin and Alex's teams have been working on. Both the payloads and avionics and recovery teams are working on that configuration specifically, because that's something that NASA's going to want to see, that we have this down and we can actually get our parachutes out. They're going to want to see that. So.
Yeah. How long is the payload? Because it seems like unless you do a really, really deep sand on it and it's kind of loose in there, you're going to have a lot of issues with getting it to eject as well as the parachutes.
I know right now with the legs, I think it's about 9 inches tall with the legs folded up. But I think it could probably, I have a little bit of extra space because I accounted for a little bit bigger batteries and a little bit more space in the middle compartment of the payload. So it could probably become 8 inches. But that's about as small as I can make the payload, is 8 inches tall.
Yeah, you might
with
want
the
to
legs.
consider putting it closer to an area it could get out, because it's going to be, I mean, I'm not sure your mass estimates yet, but 3 servo or 4 servo motors in it. It should be pretty
there's
hefty,
4 servos.
right?
Yeah, it's 4 pounds.
Yeah, so that's going to be really hard to push out the tube, especially, yeah. I mean, I'm not sure your exact ejection setup. Is it shooting out next to the avionics bay, or is it shooting out the other direction? Like around the nose cone.
Matthew, do you want to answer this?
Can you repeat that one more time? Just so I make
so
sure.
yeah, where are all the separation points on the rocket?
Yeah, I was gonna ask that too.
Oh,
So
okay.
3
Sorry.
parachutes.
Yeah. Yeah. So we have a separation point up by the nose cone, as you can see.
Hold on, just to interrupt you. You can annotate on the screen if you think that would help out a little bit.
Cool. So we have a separation point over here by the nose cone, and we have a separation point by the av bay here. So those are the current separation points on the rocket.
Is it on the bottom of the av bay or the top of the av bay?
So at the moment, it's at the top here.
Okay.
It's on the aft.
Yeah, it's on the bottom.
Oh,
yeah,
okay.
so
Sorry.
if you're trying to
Sorry.
pull that payload through like 20 inches of tubing, you're going to have some serious problems.
Okay.
Yeah, because if you've ever tried to like push a bore into a hole or whatever, I'm not sure I forget the exact terminology, but if you have the angle off just a little bit, it's not going to pull. So it's either that payload's going to have to be really loose into the tube, which is dangerous while you're flying, or you're going to have to move the payload up and the parachutes down, or move around your ejection setup.
But we also have to consider the failure mode, and that's if the payload doesn't deploy and the payload's in the back, then our main parachute still comes out, so we don't have an issue. But if we have the payload in front and we have the main parachute behind that, then if our payload gets stuck, we have another missile in the ground. So definitely something else to consider as well.
So your payload is coming completely out of the rocket then at that bottom separation point? Is that the plan?
At the top separation point.
At the top. Wait, so it's going out by the nose cone? Okay,
Yes.
following those parachutes?
That's right.
So it's coming out that
that's-
main then? Is that the plan?
It's going to be a little bit.
Yeah.
I'm sorry.
I think
Yeah.
you guys are underestimating the amount of pressure that it's going to require to push that far.
It's like you will destroy your av bay before, or you'll destroy your avionics bay before you'll push that payload out, for sure.
Okay.
Yeah,
Yeah, definitely
you might
reevaluate
want to
that.
rethink your ejection sequence.
Maybe even
Yeah.
add another section. It seems like you guys have room.
For another separation point?
Yeah.
Okay. Yeah, thank you. That makes sense.
Okay,
Yeah,
so is this the end of SL?
Yeah, we're running a little bit low on time, so we can move on to IREC.
Sure, I'll try to keep it quick. Okay, so here's my first slide. If you're at the IREC like sub-team super powwow thing, you'll already see most of these slides, but I'm going to go over them again because not everyone was there. So basically, if you are ever confused about how ejection works in rockets, here's a little diagram. We were just kind of talking about it. So we're going to be launching the rocket. We're going to be ascending. Our active controls is going to deploy. For SL, active controls won't be deploying because they don't have active controls. But yeah, it's a similar concept. It goes up. Drogue deploys, which is a smaller chute, so it slows down the rocket. Active controls will retract, and then the main will open up at like 500 feet. And you do this to limit the amount of drift that you have on the rocket. Next slide. Oh, can I control it? Yeah, so here's my avionics and recovery bay. So basically the idea is that we have this 3D printed sled, which is just like ABS. We're gonna print it out, and then it has these like little slots on the side of it. So we can basically make an entire little system onto each of these plates. So like you see that the empty plate, like we could put whatever we really want onto that plate, and we could just throw it into the av bay. So it's like super modular design, and like the wires that you'd be getting from that section can go to the terminals. I'd explain more about the avionics. Actually, do you mind if I share my screen or no?
Yeah, you have access. You should have access still.
Okay. This will stop other sharing. Okay.
You're good.
Yeah. So here's the design right now. I'll just explain a little bit about the switch setup and how all the electronics works because it might be confusing you. And it's also applicable to SL if you're part of that. So basically on the outside of the rocket, you have these like little switches here, which is these guys. Basically you could turn them in and out, and that turns your altimeter on and off.
You're cut now.
You do that from outside the rocket. The reason you do that is because if you turn on the altimeter, it's unstable. That's not good. You guys hear me? Hello?
You're back now.
Okay.
You gotta repeat that real quick.
Yeah.
Okay, yeah. So basically, these switches on the side, you could turn with the screw, and using that screw, you're able to turn on the altimeters and turn them off. So that's useful because altimeters work on pressure. So if you don't do that and you just put them in, they will activate and say, oh, I'm flying now, before you actually start your flight. So yeah, you want to be able to turn them on as soon as you get to the pad, because you don't want to be messing with electronics like on the ground, because the altimeters also control the ejection charges. So if you turn on your altimeters prematurely and they detect a flight, and then they're like, okay, flight's over, they'll blow up. And that could really hurt someone. So you have to be able to activate them on the pad. So that's why you have these switches here. And then these like little boxes, these are just the altimeter. And then super go into like how it looks electronically. But the basic idea is that it's a board, you screw it down into something. So we're screwing it down into a little fiberglass plate. And yeah, so those have wires that come out and go to these terminals here. So these terminals basically separate pieces of the rocket, so you can have wires go to them and then wires come out of them. And it's useful for not having super long wires that could get like really messy. So you can have a constant connection between this terminal and this terminal, and then also be able to reconnect it up here in a much easier fashion than you would otherwise. So yeah, those come down to here, and all the other electronics that we have would be coming down to here. All the other like ejection charge type stuff would be coming down to here. And then it'll have little holes that are airproof so that no ejection charge gas could get into your avionics bay, because that'll absolutely destroy the electronics. And also explosions have quite a bit of pressure, so that will tell the altimeters wrong data about your apogee, and that could really also set off other explosions that you don't want to happen yet. So it's, yeah, basically you want to make sure that your avionics bay is pressure proof. You could put like some sort of like epoxy or caulk or something. But yeah, so, and then this guy right here is the shock cord attacher. It's called an I-bolt actually, but basically you just attach your shock cord there, and then out of that shock cord will come your parachute. So 2 parachutes. I'll explain more about that in a second. And then, so your like little explosions that are coming from the altimeters will go into these little guys. These are made of aluminum, and we can make them super easy. Basically, you put in a bunch of black powder, you put wadding to make sure that it's not going to be shifting around during flight. And then your altimeter says, okay, it sends it basically just sends an electric current through a little piece. And that piece, as soon as it gets current, it blows up. And then that blows up the rest of the little black powder that you put in here. And that releases enough pressure to separate pieces of the rocket. So if you're ever confused about how the rockets are actually separating, that's how she's done. And yeah, so other things that we're doing right now. So we want to find some use for this panel right here. And as you can see, we also have more room up here. So I've been thinking of maybe trying to talk to other clubs to see if they want to throw anything into a rocket. I'm not sure, maybe talk to a biology club, see if they want to just put some random stuff in here. But one project that I've been kind of overly dedicated to is trying to get a camera to work in it. So if you could watch the rocket, that would also be super cool, because usually you can only watch it from the ground. So you can only live the excitement once. But I want to be able to look at this rocket and live the excitement multiple times. And also, it'll ensure that our active controls air brakes actually deploy. So we could get to watch them deploying, and we can have more data regarding how they did. And yeah, I think that's all I got for me. So yeah, in our sub-team meetings, we're going to be talking about the camera design, hopefully getting way more into it than we did last year. We're probably going to be making some sort of shrouding on the outside of the rocket, so it's nice and aerodynamic, because this section is actually close to the top of the rocket. So any sort of weird things on the outside of the rocket that we make are going to be pretty detrimental to actually how the rocket flies, because pressure near the nose cone has got to be kind of constant, or you can blow off all the mojo. I don't know. I'm a mechie. I'm an aero. But yeah, do you want to switch back to the PowerPoint? Cool.
What altimeters are you planning to use for IREC?
We're using Easy Megas. So I know that SL is using the SL 100s. Basically, the Easy Megas are similar. I'm not really 100% sure how they differ yet. I'm pretty sure I read that they're more accurate, and they have more modes. So they have like built-in modes for certain types of ejections. But aside from that, some of the Easy Megas, it depends on which type we use. Some of them have like radio things that they can send back to the ground. But yeah, they're pretty similar to the SL100s.
Yeah, the SL100s have been out of stock for the past like 6 months or so. So we may possibly for SL be moving altimeters as well.
Well, you guys can't break them because they're expensive. I gotta break them all myself. Anyways, so yeah, we were talking about how SL deploys earlier. Hey, Dylan.
Sorry, I'm gonna refresh the slide. It needs to get updated.
Okay. Oh yeah, if you have any questions.
Yes, feel free to interrupt at any time. I mean, that's why we have these. We want people to ask questions, especially questions that we don't necessarily have answers to for a design. And that's how we can really develop our designs.
Yeah, if literally anything you don't understand, just ask, because we've all been there before. And at the start, rocketry can be really confusing, but once you get the ropes, it comes through. But you got to ask the questions to actually learn the ropes, right? But yeah. Oh, go back. Uh-oh. We're in purgatory. Okay, great. So our bay, basically you usually have 2 different deployments. So you have one big separation for your drogue to come out, and then one big separation for your main parachute to come out. But we're going to be doing a singular deployment. So it'll all come out together, but the main will stay wrapped in like a wrap. while the drogue opens, and hopefully Tyler's parachute or Tyler's payload will control the drift of that drogue, so we'll be able to put ourselves places. Usually under those circumstances, like if his payload was to be 100% successful and we knew it would be successful, we'd only really need one parachute. But for safety, we have a main parachute as well instead of just one big parachute. But yeah, so our main is going to be deploying using probably a tender descender. But I've been thinking maybe we could make something on our own so we could be like, super cool and innovative. We certainly probably have the time to, because we're already starting construction based on the design that we finished last year. So yeah, there's also other things. There's chute releases. There's something that I think. You guys were talking about releasing a parachute. There's also things that have automatic cutters. So like you lead an ejection charge to it, and instead of it being a knife that you're extending out, it's like a contained knife that's not going to kill someone, even though your knife probably wouldn't either. So it's basically a pair of scissors. So yeah, we could do that and like maybe cut a zip tie or something to open up the chute. But right now we're kind of focused on the tender descender. Next slide.
All right, hey guys, I'm the new flight dynamics lead. A lot of the work for flight dynamics has been done by Matt last year. So one of the things I want to do is help with the ACS system, or ACS. And one of the ways I want to do that is I want to simulate the drag on the fin. This is like a really crappy slide that I found from a presentation. Sorry for the pixels, but this is essentially what the ACS looks like. It's essentially like 3 fins that pop out continuously. And I want to basically measure like I said, I want to measure the drag. And then I want to potentially, if I could talk to Dr. Lind over the weekend or on Monday, I want to potentially try to see if I can run that in our MATLAB simulation so that we can kind of get like another approximation for like when to deploy the ACS and like what's a good time to use it. So meeting probably on Tuesday. Time to be decided.
ACS is active control system, by the way.
Oh.
Yeah, and if you have any burning questions for either subsystem, now's the time.
Is the MATLAB simulation something that you have like free access to modify, or is that strictly
Free
Dr. Lind's? Okay.
No, I have free access to modify it. It's just like last year it had a numerical error and he didn't tell me. So like I was like running around like a rat, not knowing what the hell was going on. But I did a MATLAB, I did an internship with MATLAB this summer, so I feel like a lot more confident to work with MATLAB.
Blal or Adam, can you answer the question that's been sent in chat?
It's about Mises. So yeah.
I couldn't even read it. I'm not gonna lie. I just wanted to show you the picture as like what ANSYS kind of looks like. It's a very bad picture, though. I'm sorry.
The toast is done. So other IREC news, if you guys came out to our Payloads meeting, we were literally just sitting there for like 2-3 hours, just shooting bad ideas at each other, trying to get something to work.
A bunch of monkeys.
Throwing together ideas. But honestly, that's how the best engineering is done, by horrible ideas. And eventually, one of those horrible ideas will stick. So yeah, that's what we did. We're going to be probably doing that again shortly. So they don't have to be good ideas. If my ideas are any sort of testament to that. Basically, we just need more people to come in and tell us what we should be doing. It was great. It was real fun. And yeah, so come to the next meeting, throw more ideas onto the pile. Eventually, maybe we'll be able to combine one of them to be actually usable. Anything else, Tyler, on that?
Yeah, Tuesdays at 7, by the way.
Tuesdays
but yeah,
at 7.
We're basically trying to solve like a rotation problem and 2 different tangling problems all at the same time. And it's fun. So yeah, lots of brainstorming to do.
And then Adam, do you want to announce the new lead?
Yeah, so some news for IREC. We had been looking for a structures lead for a while, and we finally have one. His name is Gavin. So be on the lookout for structures sub-team meetings to start back up. The main thing they're going to be doing is they're going to be assisting the other sub-teams with any structural analysis that they need. And then once we're able to get back into the lab, we're going to start finishing up the manufacturing for the rocket that we began in spring. And then Bilal also has a announcement here, intro to flight dynamics meeting on Tuesday. The time will be determined later.
Yeah, I'm gonna shoot when to meet like right now. It's better that we do it with when to meet rather than I pick a time. So
Sounds good.
Speech, Gavin?
I'm excited to be a part of the team, and I'm still looking forward to kind of figuring out what there is to do and get caught up with what was done the last few semesters. But yeah, I'm really pumped.
Awesome.
Okay.
Do we have any sort of idea about how the AC meetings are going to work yet? Adam and Paul?
you know a guy named Shahir?
So for the active control
Okay,
meetings, we are currently looking for a lead for that team as well. The previous lead had to step down for personal reasons. So for the time being, I guess me and Bilal can tag team those sub-team meetings until we find somebody to take over. Once me and Bilal meet and talk about it, we'll shoot out a when to meet for that as well. We might also combine that sub-team meeting with Bilal's flight dynamics meeting.
Yeah, that was what I was like planning on doing.
Okay, so I think that's pretty much it. Thank you for coming to our second GBM of the semester. Here's all of our plugs for everything: our Slack, Facebook, Instagram, Twitter, and our sign-in. So I'll leave the floor open to any questions, but if we don't really have any for a little bit, that'll be the end of the meeting.
Real quick, if anyone knows any companies or has like a brother that works at a company that wants to help us with sponsors, that'd be very great if you just suggest like a company or anything, or give us like their email, just so that we can try to like send them like a quick email, ask them, hey, do you want your logo on our shirts or something, like, or on our rockets? So
Yeah, and just as a quick reminder, on Slack, it's really good to join pretty much every single sub channel there is, so then you can get updates from everybody. Most of the teams are pretty good at announcing when they're going to be meeting, along with doing it in the general chat, but there's a lot more focused discussion in each individual channel if you want to figure out what everybody is doing and like the process that they're going about doing everything. So this will be the last call for any questions. Just speak up in chat or type it out. Okay, if not, this is the end of the meeting. If you want to watch it back, it'll be posted on YouTube and we'll post the slides on Slack. But otherwise, thank you for coming out. And we'll see you guys again in probably 2 weeks.